Okay, I want you to picture this. A massive, 100,000-ton steel cargo ship is miles out at sea, leaning aggressively into the absolute onslaught of a vicious, towering storm. Waves are crashing against its hull, pushing it to seemingly impossible angles. Now, by all common logic, thousands of tons of heavy steel should just plunge straight to the bottom of the ocean, right? Yet, time and time again, the vessel somehow rights itself. What you're witnessing out there isn't just luck. It's an invisible, high-stakes battle between gravity pulling the ship down and buoyancy fighting to keep it upright. Welcome to today's Explainer, where we're going to uncover the hidden geometry of fluid mechanics that keeps us afloat.
It's a question that civil engineers, naval architects, and structural designers have to answer with absolute mathematical certainty. A miscalculation here doesn't just mean a poor grade on a project, it means catastrophic failure. We're talking about the fundamental physics of not sinking. It's literally a matter of life and death, governed by forces you can't even see. So let's dive into this and unpack the hidden physics of staying afloat.
Section 1. The forces of flotation, center of gravity versus center of buoyancy.
To really understand why a ship survives a storm, we first need to look at two foundational forces locked in a constant tug-of-war. First up, we have the center of gravity, or G. This is the exact point where the entire downward weight of the object is concentrated. Pulling directly against that is the center of buoyancy, B. This one is the centroid of the displaced liquid. Think of the water being pushed out of the way by the hull. Well, the upward counterforce acts right through the geometric center of that space.
All right, moving to Section 2. Stability of submerged bodies, submarines, and balloons.
Before we tackle a bouncing surface ship, let's consider bodies completely surrounded by fluid. Think of a submarine diving deep underwater or a weather balloon floating way up in the atmosphere. In these cases, the volume of the displaced fluid never actually changes shape, which means the center of buoyancy, B, is completely locked in place. If an underwater current tilts that submarine, B and G are suddenly no longer vertically aligned. But because B is engineered to be physically higher than G, this shift creates a restoring couple. Basically, a rotational force that twists the submarine right back to an upright, level position.
So the absolutely crucial point here is that for a totally submerged body, survival comes down to one golden rule. The center of buoyancy must be permanently located above the center of gravity. If B ever drops below G, the second that submarine tilts, those exact same forces will create an overturning couple, flipping it completely upside down into unstable equilibrium. And nobody wants that.
Section 3. Enter the metacenter, the geometric hero of floating bodies. Now, here's the twist. Surface vessels act completely differently. Because they sit right on the surface, the water level physically cuts across the hull. When a ship tilts, its underwater shape actively changes. While G and B might be perfectly stacked at rest, a tilt pushes one side deeper, physically shifting that volume of displaced water. The center of buoyancy actually moves to a brand new location, which we call B1. And this brilliantly illustrates our next concept. If you draw a straight vertical line up from this new upward thrust at B1, it intersects the ship's original vertical axis at a very specific point. That point is M, the metacenter.
The metacenter is the ultimate pivot point for a surface vessel. For small angles of heel, when the ship is just rocking back and forth, this point M acts essentially like a pendulum's pivot. The entire stability of a floating ship is dictated by exactly where this invisible point hovers in space. It is quite literally the geometric hero preventing a massive disaster. Section 4. Stability of floating bodies, the restoring couple. Because the center of buoyancy shifted, the rules for survival fundamentally change. Remember how for a submerged submarine, B had to be above G? Well, for a floating surface ship, B is actually allowed to be below G. Instead, the metacenter, M, steps up to the plate. Think of this as the ultimate cheat sheet. As long as M remains above the center of gravity, the ship is in stable equilibrium, creating that righting couple that snaps the ship back upright. But if M falls below G, the ship capsizes. No way around it.
Section 5. Calculating metacentric height, the experimental and theoretical methods.
Let's move to how this actually builds in the real world. Knowing that M needs to be above G is great in theory, but naval architects have to literally prove it by finding the metacentric height, or GM. To find this experimentally on an actual vessel, engineers will place a known weight right in the center of the deck and then slide it transversely by a specific distance. This purposefully forces the ship to tilt.
Then, using a plumb line hanging inside the ship, they measure the exact angle of heel. By plugging the weight, the distance moved, and that angle into a very specific formula, they can pinpoint the exact metacentric height.
But actually, scratch that. Before a ship is even built, engineers rely on the theoretical method. This formula right here, gm equals I over v minus bg, is the mathematical guarantee of a ship's stability. I is the moment of inertia of the ship's waterline. A wider ship has a massively higher moment of inertia which pushes the metacenter higher. V is the displaced volume. So by balancing the physical shape of the hull at the waterline against the overall weight distribution, designers can physically program the ship to resist capsizing from day one.
Which brings us to Section 6, the mathematics of rolling, balancing safety and comfort.
Now, what's really interesting about this is that fluid mechanics isn't just about preventing a ship from flipping over. It's about what happens dynamically when the ship rolls. The rigid calculation of that metacentric height directly dictates the physical experience of everyone on board. Take a look at the formula for T, the time period it takes for a ship to roll from one side to the other. Notice that the metacentric height, gm, is in the denominator. This inverse relationship means if you increase gm to make the ship incredibly stable, you get a much smaller T. That translates to a very short, very fast, and quite violent rolling period.
And this creates a truly fascinating engineering trade-off between absolute safety and human comfort. Warships, for instance, which might suffer hull damage in combat, are designed with a very large GM, sometimes up to 1.5 meters. They are phenomenally stable, but that huge GM causes a tiny rolling period. The ship just snaps violently back to upright, which places immense strain on the structure and throws the crew around. On the flip side, passenger cruise ships are deliberately designed with a much smaller GM. While they have slightly less absolute stability, it results in a much larger time period. That gives you a long, slow, comfortable roll that keeps vacationers from getting terribly seasick.
All right, let's pull all of this together. We've journeyed from the physical threat of a raging storm right down to the exact fluid mechanics that save the day. For completely submerged objects, the center of buoyancy just has to stay above gravity. Simple enough. But for floating bodies, it's all about that shifting volume of water creating the metacenter. As long as M is engineered to sit above G, the resulting righting couple will fight back against the waves. And that exact distance between them, the metacentric height, forces engineers to perfectly balance a vessel's survivability against its everyday dynamic performance.
So, the math behind these textbook principles, it isn't just theory. It is the invisible geometry that quite literally commands the oceans. Whether you're a civil engineering student mapping out your very first hydrostructure or a seasoned professional evaluating real-world stability, these formulas are the exact tools that hold chaos at bay. The real challenge for us is this. How will you balance that equation of absolute safety against dynamic performance in your next project? Thank you so much for exploring the depths of fluid mechanics with me today, and keep looking for the physics hidden just beneath the surface.